In algebra, a relation is a mapping of one number to another number. So if I write an ordered pair, and this is called an ordered pair because the order matters, and a pair because there's two numbers. So if I write an ordered pair, say 3, 5, we normally call the first variable x and the second variable y. We can use other letters, but most often we use x and y. And what that means is that if I start with the number 3, that maps to the number 5. So if I have a list of ordered pairs, and I'm just making these numbers up, they really don't have any mathematical significance. I'm just completely making them up. That means that 7 maps to -1 and -2 maps to 4. We call the set of all the x's the domain. So in this case, my domain, and I'm going to use these symbols, this means the set of, so the domain is the set of the numbers, and we normally write them in numerical order. So -2, 3, and 7 are the three numbers that we've used as x's. The range is all the values of y, all the numbers that are being mapped to. So I write my set notation, and I have the numbers -1, 4, and 5, because those are all the numbers that are being mapped to. We're going to be primarily interested in this class in functions. So a relation is any mapping from an x to a y, from an input number to an output number. But a function is a special kind of a relation. So a function is a relation in which every x maps to exactly one y. That means that if I say start with, say, the number 7, what does 7 map to? There's only one answer. There's only one y that it maps to. So if I see 7 only maps to -1, 3 only maps to 5, and -2 only maps to 4. So this relation is a function. And there is another way that we can show this same information that I have up here. If I know that it is a function, this is a function. If I call this the function f, then I can rewrite this using what's called function notation. I can say f of the starting number, that's how I would read this, f of 3. So this symbolism, f parenthesis 3 close parenthesis, is read as f of 3. And that's just saying, what does the function f map the number 3 to? So f of 3 maps to 5. So f of 3 equals 5. F of 3 equals 5 gives me exactly the same information that this ordered pair does. These two are equivalent. And there's yet another way that I can show that same information using a coordinate system. If I start with the number 3, this axis is a number line for x. This axis is a number line for y. So if I'm plotting the ordered pair 3, 5, I start with 3, I go out to 3 on the x-axis, and then I go up to 5 on the y-axis, and I plot that point. So this point, this ordered pair, this ordered pair, this arrow notation, and the function notation all give me exactly the same information. Pause the video and rewrite each of these other two ordered pairs using function notation and plot those ordered pairs. And when you're finished with that, go ahead and restart the video. Okay, so we see that the ordered pair 7, negative 1 is the same thing as f of 7 equals negative 1. And the ordered pair negative 2, 4 is the same thing as f of negative 2 equals 4. And then if I plot both of those ordered pairs, I come out here to 7, and then I go down to negative 1, and I plot that point. And then negative 2, 4, I go left here to negative 2, and then up to 4, and I plot that point. So these 3 dots, these 3 points on the coordinate system, these 3 ordered pairs, and these 3 function notation statements all give me exactly the same information. And I can actually do this backwards as well. For instance, let's say that I didn't know any of this. All I had was the graph. So let's say that I'm just given this function as a graph, and I want to know, and I'm told that these 3 dots, and this is not a very interesting function because it is literally just these 3 dots. We can't connect anything in there. We can't extend any lines. These 3 points literally are the entire function. And let's say that we call that function represented by those 3 ordered pairs f. So if I wanted to ask you what is f, for instance, of 3, what I would do is go out to x equals 3, and then I would look up and down, straight up and down from x equals 3, and I would see where does that imaginary line cross the function. And I have this point right here on my function. So I would say, okay, if I'm starting with x equals 3, my point is here, I come across, and what is the y that goes with that? And in this case, it's 5. So then I would know that f of 3 equals 5. And then I could do the same thing with various other numbers. For instance, I could find f of 7, and I could find f of negative 2. So you go ahead and try not to look back at the earlier function as it was defined. Look at the picture, draw your mental, you don't have to actually draw it, but mentally look up and down from, for instance, x equals 7, and then across to what y equals, and find these other 2 function values. Pause the video, do that, and when you're done, start the video again. Okay, so f of 7, we come out here to x equals 7, we come down, and we come across, and we see that f of 7 is negative 1, and then f of negative 2, we come out to x equals negative 2, we go up to where it crosses the graph, we come back across to what the y value is, and f of negative 2 is 4, which is, of course, what we had earlier. Let's look at something else, though, here. What if I asked you, what's f of 5? F of 5. This number inside the parentheses is always your x. So I'm saying if x is equal to 5, what is y? So if I try to come up here, and I come out here to x equals 5, and I look up and down from x equals 5, I see that I never touch the graph anywhere. I never touch any of those 3 ordered pairs. So that means that f of 5 does not exist. And that's because, remember earlier, we figured out what our domain was. Our domain is all of the x values, and our domain was -2, 3, and 7. The number 5 is not in the domain. So I cannot find a function value for 5 because it is not in my domain. If I draw a line up and down from 5, okay, let's pretend that touches 5 here, it never touches the graph anywhere. Also notice on this, because it is a function, any place that I draw a vertical line straight up and down either doesn't touch the graph anywhere or only touches it in exactly one spot. So that tells me for every value of x, there's a single value of y. And that's because it is a function. This is what's called the vertical line test. And that's if a vertical line drawn anywhere on the coordinate system touches the graph no more than once. So 0 or 1 time. All right, so that's the vertical line test. Now, what I'm going to do is I'm going to give you a couple of other relations, and I would like you, I'm going to write them as ordered pairs. And what I would like you to do is basically what we've done on this one, is I want you to write each one, I want you to plot all of the points on each one. I want you to determine if it is a function or not a function. And then if it is a function, I want you to write it using function notation. Oh, I'd also like you to find the domain and the range of each one. So I'm going to give you the earlier one we called F. Let's call this one G. And I'm just going to make up some numbers again. There's nothing really important about these numbers. I'm just making them up. So I want you to do the arrow notation. I want you to graph it. In other words, plot the points. I want you to write the domain and the range. And then I want you to determine if it is a function. And if it is a function, then write using the function notation. So I'm going to do G, and then we're going to do H. And I want you to do the same thing for it. So pause the video, spend a few minutes doing all those things, and then turn the video back on. All right, let's look at relation G. With my arrow notation, I have 0 is mapping to 3, -3 is mapping to 4, and then 5. And notice that I have my y is 3 again. So I already have 3 listed. So my 5 is going to map to 3 as well. So I see that my domain is the numbers -3, 0, and 5. Oops, there should be a set notation. And my range is just the numbers 3 and 4. So if I graph that, I didn't really leave myself enough room to graph it here, so I'll squeeze that in. If I graph that, all right, so I have 0, 3. Now, when x is 0, I'm right here on the axis. I'm not going to the left or the right at all, but I am going up 3. So that's this point right here. Then I have -3, 4. It's right here. And then I have 5, 3, right here. And if I try to determine whether this is a function or not, I can use the vertical line test, or I can think, do I have a repeat of my x's? And I see that I have 0, -3, 5. I never repeat my x. In my vertical line test, I never cross the axis or the graph anywhere more than once. So this one is a function. So that means I can write my function notation. F of 0 equals 3, f of -3 equals 4, and f of 5 equals 3. So each time, if I say, what does 0 map to? It maps to 3, one number. What does -3 map to? 4, one number. What does 5 map to? 3, one number. So it's okay if my y repeats. This is still a function. Let's look back at my relation h. If I do my arrow notation, 2 maps to 4, 3 maps to -2, and then here I have 2 mapping to 5. So I see this number 2 maps to a different y. So I have one value of x, 2, mapping to 2 different values of y. That means that this is not a function. And there's a couple of ways I can see that. If I were to graph this, I have the point 2, 4. And the point 3, -2, and the point 2, 5. And notice that if I try my vertical line test, I am touching the graph 2 times, which gives me 2 different values of x, 4 and 5. So I can see that this is not a function using the vertical line test, or by noticing that my x repeats here in my ordered pairs. And if I wrote my domain, I have 2 and 3 are my only 2 numbers. In my range, I have -2. And again, I put these in left-right numerical order. That's the normal way you do that. And if you have the same number twice, you don't write it twice. You just list it one time. So what we've looked at in this lesson is some pretty specific relations that were just lists of ordered pairs that I just made up. And we saw how to write that with arrow notation, how to determine whether it was a function or not a function. If it was a function, we could write using function notation. I can't do that on this h because it is not a function. We learned how to plot the points, and we learned how to identify the domain and the range. In the next video, we're going to look at a lot of those same concepts, but we're going to do it using more, shall we say, interesting relations.